Google's Willow quantum processor completed a benchmark calculation in under 5 minutes. By Google's own estimate, the fastest classical supercomputers on Earth would need roughly 10 septillion years to do the same task. That is not a typo-sized exaggeration, it is a number so far beyond the age of the universe, about 13.8 billion years, that it stops functioning as a normal comparison and starts functioning as a kind of rhetorical device. When a gap becomes that extreme, it invites a bigger question than how fast is this chip. It invites the question of what, exactly, is happening inside it. That question has led some commentators, and a smaller number of physicists, toward one of the strangest ideas in modern physics. The possibility that quantum computers do their work not merely within our universe, but by drawing on other branches of reality entirely. It's a genuinely fascinating idea, and it's worth taking seriously as a piece of physics history. It is also, as of today, unproven, and the distinction between interesting interpretation and demonstrated fact is the most important thing to keep straight while thinking about Willow. What Willow actually is. Willow is a 105-qubit quantum processor. To understand why that number is significant, it helps to start with what a qubit is not, a bit. Classical computers, from smartphones to supercomputers, run on bits, switches that are either on or off, 0 or 1. Every photo, video, and spreadsheet you've ever opened is, underneath everything, a very long sequence of those binary choices. Qubits behave differently. Through a property called superposition, a qubit can exist in a combination of 0 and 1 states simultaneously, rather than being locked into one or the other. When multiple qubits become entangled, linked in a way that ties their states together regardless of distance, the resulting system can represent and manipulate a staggering number of possible configurations at once. This is the source of quantum computing's theoretical power. It doesn't check possibilities one at a time, the way a classical processor does. It works with many of them in parallel, using a phenomenon called interference to amplify the paths that lead toward a correct answer and cancel out the paths that don't. The task Google gave Willow is called random circuit sampling. It's a deliberately brutal benchmark, designed specifically to be nearly impossible for classical machines while remaining tractable for a well-built quantum processor. It doesn't solve a practical, real-world problem like discovering a new drug or modeling the climate. Its entire purpose is to stress-test the boundary between what classical and quantum machines can do. Willow crossed that boundary by an almost absurd margin. This isn't the first time Google has made a supremacist-style claim. In 2019, the company's Sycamore processor made a similar announcement, and it was met with real pushback. Several researchers argued that smarter classical algorithms could close much of the gap, and to some degree, they did. Willow's advocates argue the situation is different this time because the scale of the gap is no longer just large, but astronomical, making it much harder for classical computing to ever catch up through cleverer algorithms alone. That said, it's worth noting that supremacy claims have a history of being contested and revised, and Willow's results should be read with that history in mind rather than as a permanently settled fact. The stranger question underneath the speed. Quantum mechanics has always resisted common sense. A particle can behave as though it occupies several possible states at once, and only when it is measured does it settle into a single, definite outcome. Physicists have debated what that actually means for the better part of a century, and there is no single, universally accepted answer. The most widely taught view, the Copenhagen interpretation, treats those unmeasured possibilities as mathematical, waves of probability that describe what we're likely to observe, not separate physical realities in their own right. On this view, a quantum computer is an extraordinarily precise probability manipulation machine. It doesn't need other universes to explain its power. It just needs the strange, well-tested mathematics of quantum mechanics, applied with more control than we've ever managed before. The many worlds interpretation offers a far more radical picture. In this view, when a quantum system has multiple possible outcomes, all of them actually happen, each occurring in its own separate, equally real branch of reality. A particle that could go left or right doesn't choose one path when measured. Instead, reality itself splits, with one branch containing a version of events where it went left and another where it went right. Extended to a quantum computer, This interpretation suggests that a chip processing many possibilities simultaneously might be doing so because those possibilities correspond to genuinely distinct branches of reality, with a final answer emerging from interference between those branches. It's an idea that has been taken seriously by credentialed physicists for decades. This isn't fringe science fiction speculation invented for a headline. But it's crucial to be clear about what kind of idea it is: an interpretation. Many worlds and Copenhagen, along with several other interpretations, such as pilot wave theory, make the same testable predictions about what we'll observe in every experiment performed so far, including Willow's benchmark. That's precisely why the debate has lasted a century. There is currently no experiment that can distinguish between these interpretations, because they were constructed specifically to agree on all observable outcomes while disagreeing on the underlying picture of reality. Willow producing a fast, correct answer is fully consistent with Copenhagen. It's also consistent with many worlds. It doesn't favor one over the other. What Willow did demonstrate. Setting the multiverse question aside, Willow's more grounded and arguably more important achievement involves error correction. Quantum systems are notoriously fragile. Qubits are disturbed by heat, vibration, and stray electromagnetic noise, and that disturbance can corrupt a calculation before it finishes. This fragility is the main reason practical, general-purpose quantum computers have remained elusive despite decades of steady progress. Historically, one of the biggest fears in the field has been that as you add more qubits to make a system more powerful, you also add more opportunities for errors to creep in, meaning bigger machines could become proportionally less reliable. Willow appears to push back against that fear. Google reported that as the chip scaled up, error rates went down rather than up, a sign that certain error correction techniques were successfully suppressing the noise that normally plagues these systems. If that trend holds and continues at larger scales, it would represent a meaningful step toward quantum computers that are not just fast in short bursts, but stable enough to run long, complex, practically useful calculations, the kind that could eventually contribute to drug discovery, new materials science, more detailed climate modeling, or advances and threats related to encryption. That's a